Welcome friends, myself Gaurav Gandge from Paloti College of Engineering and Technology. Today we are going to study the rules for source transformation. Let us start with this. Heading as source transformation. As we know, voltage source is represented as series impedance and a voltage value, say V. Then current source is represented as current I and parallel connected impedance. So these are the two sources and their representation. Now let us understand the source transformation. When we are to transform voltage source to current source, where to find the value of current, which is find out by using voltage and impedance that can be found from voltage source. So voltage source consists of voltage and its series impedance. So therefore this I is equal to, using simple Ohm's law, V upon Z. This is Ohm's law. When we have to transform current source into a voltage source, using same Ohm's law, we get V is equal to. Now we have to find out the value of voltage from current source, which consists of I and Z. So it gives you I into Z. So again, the rule, the law which is used to get this particular equation or the value of voltage V while doing this current source to voltage source is V is equal to I to Z. Okay. So in both the cases the Ohm's law is used. The only thing is we have to decide the conversion, whether we have to convert voltage to current or current to voltage source, and accordingly we have to find out the unknown parameter. Now consider third circuit. In third circuit, if two voltage sources having impedance Z, one for first source and V1 is the voltage value, Z2, so I just write it here, this is Z1 with V1, Z2 with voltage source V2. So when we have this kind of series connection, its equivalent circuit gives me what? As okay, so I first just draw this circuits and then we'll see the explanation. Okay, now just check. This V1 and V2 both are connected in series. So its equivalent is what? V. This can be calculated using Kirchhoff's voltage. So V1 and V2, its equivalent is V is equal to V1 plus V2. Okay. Now if we just see the impedance connection, Z1 and Z2, both are connected in series, and for series connection its Z equivalent impedance is Z1 plus Z2. This is Z1 plus Z2. Okay. So please remember, as we have two voltage source V1 Z1, V2 Z2 connected in series, we get the equivalent voltage as V1 plus V2, and Z1 Z2 represents the series connection, therefore its equivalent impedance is Z1 plus Z2. Now, similar way, just take the rule for current source. If we have a current source I1 and its internal impedance say Z1, then I2, its internal impedance is Z2. Okay. Now, just check here, current source I1 and current source I2 both are parallel connected. So at this point you have to apply what? KCL. This point is the meeting point of I1 and I2, which gives me its equivalent current as the orientation would be definitely upward, as I is equal to I1 plus I2. Okay. Then these two impedances Z1 and Z2 again are parallel to each other. So it gives me a parallel combination of the impedances, which is Z equivalent. But when impedances are in parallel, what we get, what we know, it is Z1, Z2. What we have? Z1, Z2 upon Z1 plus Z2. Okay. So again I am telling you, when we have a current source I1, its internal impedance Z1, parallel connected with another current source I2, its internal impedance Z2, we get the parallel connection for both I1 and I2. It gives me a meeting point, this, where both the current meets as the direction is same, and hence it gives me I is equal to I1 plus I2. Okay. Don't go with the handwriting, right? Okay. So I is equal to I1 plus I2. Then Z1 and Z2 both are parallel connected. So from parallel impedance or parallel resistance rule, we get Z equivalent is equal to Z1 Z2 upon Z1 plus Z2. Okay. So these are the 4 rules to understand, and that gives me idea about the voltage source, current source, their transformation and their series.